For centuries, humanity has gazed into the cosmic abyss, captivated by its most enigmatic devourers, black holes. We have long seen them as ultimate gravitational prisons, celestial monsters that swallow light, space, and time itself. Our questions have centered on the crushing force at their heart, the impossible densities, the very fabric of space-time being torn asunder. But what if this conventional perspective, this relentless focus on gravity, misses the true, chilling heart of the mystery? What if the deepest secret of these cosmic leviathans isn't about where the stuff goes, but where the story of the stuff goes? Our journey into this profound enigma begins not in the cold vacuum of space, nor with the grand theories of relativity, but in the quiet, methodical world of mathematics and early computing. In the year 1948, an American mathematician named Claude Shannon published a revolutionary paper titled A Mathematical Theory of Communication. It was a work that would forever alter our understanding of how data flows, how it is stored, and indeed, what it fundamentally is. Shannon quantified information, breaking it down into its most elemental unit, the bit. A bit, a simple 0 or 1, a light switch turned on or off, became the bedrock upon which our digital age was built. He revealed that information, in its purest form, is inextricably linked to entropy, the measure of disorder, and thus to the very physical world around us. This profound connection between the abstract and the tangible was further cemented in the year 1961 by a brilliant physicist working at IBM, Rolf Landauer. He formulated a principle that bore his name, Landauer's principle, a deceptively simple statement with monumental implications. Landauer proved that erasing even a single bit of information, converting it from a 1 to a 0 or vice versa, must generate a minimum amount of heat. Think of it. The act of deleting data on your computer, on a fundamental level, warms the universe, albeit infinitesimally. This wasn't just a theoretical curiosity, it was a physical law, a stark declaration that information is not some ethereal, non-physical concept. Information is a tangible entity, as real as energy, as real as matter. This insight establishes a profound, almost sacred law governing our universe. Information, just like energy, cannot be destroyed. It can only be transformed, rearranged, or hidden, but never truly obliterated. This principle is a cornerstone of physics, a fundamental tenet that underpins everything from the laws of thermodynamics to the very stability of our quantum reality. But then we introduce the black hole. This cosmic censor, this ultimate devourer, appears to defy this immutable law. It seems to consume everything that crosses its threshold, vast stellar matter, brilliant energy, and with them, all the unique, intricate information those objects carry. Consider the early computing machines, their immense, clunky forms processing data not with silicon chips, but with thick stacks of punch cards. Each hole, or lack thereof, on a card represented a discrete bit, a fragment of information contributing to a larger dataset, a story. Now, transpose that image onto the cosmic stage. Visualize entire stars, planets, and nebulae, each a colossal collection of unique, intricate information, like billions upon billions of cosmic punch cards. As they spiral inwards, drawn by an irresistible pull, they plunge into the unseen maw of a black hole. What happens to those cosmic punch cards? Does their story simply vanish? Does the universe possess a fundamental delete button, a cosmic shredder that can erase the very memory of what once was? If information, like energy, cannot be destroyed, then where does the unique identity of that swallowed star go? Where does the precise arrangement of its atoms, the history of its formation, the record of its light and heat, ultimately reside? This is the central mystery, the profound paradox that has ignited a firestorm within the heart of theoretical physics for decades. The vanishing information, the seemingly erased story, is the ghost in the machine of the cosmos. Our investigation, our relentless pursuit, is a hunt for this ghost, a quest to understand if the universe truly can forget. For centuries, the cosmic ballet has played out across the canvas of the night sky, a symphony of light and shadow. But what if, long before we truly understood the ultimate cosmic censors, humanity had already begun to glimpse their terrifying secret? Our hunt for the ghost of vanished information, that impossible erasure of cosmic stories, takes us back to a time when gravity itself was still considered a simple force, and light merely tiny, fast-moving particles. It was in the year 1783, an era when science was still deeply intertwined with natural philosophy, that an English polymath named John Michell penned a letter to the Royal Society, a missive that held a profound, almost prophetic vision of what we now call a black hole. Michell, a man whose brilliant insights were almost lost to the annals of history, employed the straightforward mechanics laid down by Isaac Newton to conceive of a celestial body so extraordinary, so dense, that nothing, not even light, could escape its gravitational grasp. He theorized a dark star, a colossal mass whose escape velocity, the speed an object needs to break free from its gravitational pull, would surpass the then-known speed of light. To truly grasp the essence of his idea, think of a rocket blasting off from Earth. It must achieve a speed of about 11.2 kilometers per second to escape our planet's gravity. Michell extended this concept to light itself, seeing light as a stream of minuscule particles, imagining a star so incredibly massive that its gravity would simply overpower these particles, yanking them back before they could ever reach our eyes, rendering the star utterly invisible. This foundational concept, revolutionary for its time, was a testament to Michell's extraordinary foresight, yet it was fundamentally different from our modern understanding. His dark star was still just an incredibly dense object within a flat Newtonian space, a cosmic trap that relied on gravity physically dragging back light particles. It was a curiosity, a theoretical oddity that fit within the existing framework of physics. However, the true monster, the terrifying space-time distortion that embodies the information paradox, would not emerge until the dawn of the 20th century, born from the revolutionary mind of Albert Einstein and his general theory of relativity in the year 1915. As the First World War raged across Europe, tearing apart nations and lives, a German physicist and astronomer named Karl Schwarzschild found himself serving on the Russian front. Amidst the chaos and desolation, an intellectual light shone brightly. Within mere weeks of Einstein publishing his groundbreaking equations describing gravity not as a force, but as the curvature of space-time, Schwarzschild achieved something truly monumental. He found the very first exact solution to those incredibly complex equations, mathematically describing what we now recognize as a black hole. It was a staggering feat of theoretical physics, performed under unimaginable duress, demonstrating the sheer power of human intellect even in the darkest of times. Schwarzschild's solution was a radical departure from Mitchell's simple, dense object. It revealed not just a star whose gravity was too strong for light, but a terrifying new feature woven into the very fabric of the universe itself, an event horizon. This was not a physical surface you could stand on, but an invisible, one-way membrane, a point of no return in space-time. Once anything, be it a ray of light, a particle of dust, or even a starship hurtling at near light speed, crosses this boundary, it is irrevocably committed to falling further into the abyss. Nothing, not even a whisper of information, could ever return from beyond this cosmic threshold. Consider a cosmic current, flowing ever faster towards an unseen drain. The event horizon marks the point where that current exceeds the speed of light itself, meaning that even if light attempts to swim upstream, it is swept away into the singularity beyond. This realization transformed the black hole from a mere curiosity into a true theoretical paradox, an absolute prison for information. It wasn't just about matter being crushed or light being trapped. It was about the very unique story of that matter and light, its intricate information, being seemingly locked away, challenging the core principles of physics that stated information, like energy, could never truly be destroyed. For decades, the event horizon had been considered the universe's ultimate barrier, a one-way cosmic membrane from which nothing, not even a whisper of light, could ever return. It was the perfect prison, the ultimate shredder of cosmic stories, holding all its secrets beyond an impenetrable veil. But what if this absolute boundary, this terrifyingly perfect wall, wasn't so absolute after all? What if, in its very structure, a tiny, fundamental flaw existed, a crack through which the universe itself could begin to leak? It was in the year 1974, in the hallowed, ancient halls of Cambridge University, that a young, brilliant physicist named Stephen Hawking began to probe this very question. He wasn't looking to break general relativity, the grand theory that described the vast, sweeping curves of space-time, but rather to marry its cosmic elegance with the bizarre, unpredictable realm of quantum mechanics, the rules that govern the universe at its most minuscule scales. His groundbreaking work would soon reveal that the black hole, previously thought to be an eternal, silent devourer, was in fact anything but. The popular science narrative often simplifies what happened next, speaking of particles just popping into existence at the black hole's edge, as if from nowhere. But the truth, as always with the quantum world, is far stranger and infinitely more profound. The underlying principle isn't about mere creation. It's about the inherent, energetic chaos of the quantum vacuum itself. Consider the deepest, emptiest void of space. Even there, it is not truly empty. It is a roiling, seething ocean of pure energy, a cosmic cauldron where the very rules of classical physics simply dissolve. Visualize space-time at the very edge of an event horizon, not as a smooth, tranquil sheet, but as a violent, frothing, quantum foam. Within this foam, pairs of virtual particles are constantly, instantaneously flickering into existence and then vanishing, annihilating each other almost as soon as they appear. One particle carries positive energy, its fleeting twin carries negative energy, always balancing the cosmic books, a cosmic loan that must be repaid in an instant. Hawking's profound insight was to grasp what happens if such a pair manifests right at the precipice, precisely at the event horizon itself. If the negative energy particle happens to fall past the point of no return into the black hole's crushing embrace, it effectively steals mass from the black hole itself, reducing its immense gravitational pull, however infinitesimally. Freed from its partner, the positive energy particle, now with no negative counterpart to annihilate with, escapes into the vastness of space. It transitions from a mere virtual fluctuation to a very real, observable particle, carrying a tiny fragment of energy away from the cosmic maw. This escaping particle is what we now call Hawking radiation. It means the black hole is not truly black at all. It possesses a faint, persistent glow, emitting energy and particles into the cosmos. Over timescales so vast they defy human comprehension. A black hole with the mass of our own Sun might take a staggering 10 to the power of 67 years to fully evaporate, a number far, far longer than the current age of the universe itself, which is a mere 13.8 billion years. These cosmic giants will slowly, inexorably, shrink and vanish. But then came Hawking's devastating conclusion, a twist that sent shockwaves through the scientific community and threatened to unravel everything we thought we knew about information. He calculated that this radiation, this faint glow emanating from the black hole, is purely thermal. Think of it like the random hiss of static from an old, detuned radio, or the indistinguishable, generic noise of a boiling kettle. It carries absolutely no unique information about the specific objects that plunged into the black hole and formed it. It is just heat, a random signature devoid of any memory. This led Stephen Hawking to his most controversial claim, a bold scientific gamble. That information, that sacred, inviolable currency of the universe, is fundamentally destroyed when it enters a black hole and then radiates away as meaningless static. If this were true, it would mean the universe truly does have a delete button, a cosmic shredder that wipes away the story of matter and energy forever. This radical assertion directly violated a cornerstone of quantum mechanics, the principle that information can never be lost, only transformed. It created what became known as the black hole information paradox, igniting a ferocious 40-year intellectual war between the giants of physics, a battle for the very soul of reality and the integrity of our physical laws. Stephen Hawking's stunning declaration that a black hole's thermal radiation carried no memory of its cosmic meal sent shockwaves through the very foundations of theoretical physics. It was not merely a scientific anomaly, it was an existential threat, a gaping wound in the otherwise perfect fabric of our understanding. For if information could truly be destroyed, if the universe possessed a fundamental delete button, then one of the two pillars of modern physics had to be fundamentally flawed. This was a direct assault on the inviolable laws of quantum mechanics, and the battlefield was instantly drawn. On one side stood general relativity, the majestic framework describing the cosmos on its grandest scales, seemingly upheld by Hawking's calculations. On the other, the intricate, often baffling but undeniably successful laws of quantum mechanics governing the universe at its most minuscule. This was not a polite academic disagreement. It was an intellectual war, with the deepest principles of reality hanging in the balance. Two titans emerged to challenge Hawking's bold assertion. From the Netherlands, Gerard Hooft, a future Nobel laureate whose intellect was as sharp as it was broad. And from Stanford, a famously pugnacious American physicist named Leonard Susskind, known for his relentless intellectual sparring and his unwavering commitment to quantum principles. For these men, Hawking's proposal was not just incorrect, it was anathema. It threatened to bring down the entire edifice of quantum physics, unraveling decades of progress and understanding. Their core argument was rooted in a concept called unitarity. Think of unitarity as the universe's perfect, unbreakable accounting ledger. It is a mathematical law, a non-negotiable principle of quantum theory, which guarantees that information, like energy, can never be lost. It can be scrambled, hidden, transformed, or diffused across the cosmos, but it can never truly vanish into nothingness. If you start with a specific amount of information, then, no matter what happens, that same amount of information must exist somewhere in the universe, albeit perhaps in a profoundly altered state. For 't Hooft and Susskind, if Hawking was right, it meant a gaping loophole in this cosmic ledger, implying that quantum mechanics itself was incomplete, or worse, fundamentally wrong. The central battleground of ideas began to form around a radical proposal put forth by Susskind: black hole complementarity. This concept suggested something truly mind-bending about the nature of reality itself, that it could be observer-dependent. To grasp this, consider an astronaut bravely, or perhaps foolishly, falling into a black hole. According to Einstein's general relativity, as this astronaut crosses the event horizon, the point of no return, they should experience absolutely nothing unusual. No sudden jolt, no tearing forces, just a peaceful, albeit irreversible, descent into the abyss, as if floating serenely through empty space. Yet, from the perspective of a distant observer, positioned safely outside the black hole's gravitational grasp, the reality of that same astronaut would appear shockingly different. To this distant witness, the astronaut would never actually cross the event horizon. Instead, they would appear to slow down, stretch out, and become thermalized, their unique information smeared and radiated away as part of the Hawking radiation, much like an object slowly burning to ash and radiating its components into the air. Suskind's profound, almost paradoxical claim was this: both realities are true, simultaneously, yet they are not accessible at the same time. The experience of the falling astronaut and the observation of the distant scientist are complementary. They are two valid, equally real descriptions of the same event, without ever contradicting each other within their respective frames of reference. It was a conceptual tightrope walk, attempting to reconcile the smooth spacetime of general relativity with the information-preserving demands of quantum mechanics. This intricate intellectual dance led to perhaps the most powerful and strange idea to emerge from these information wars: 't Hooft's holographic principle. This notion, initially considered nothing short of heretical, proposed that all the information about a three-dimensional volume of space, for example, everything contained within the crushing interior of a black hole, could be completely encoded on its two-dimensional boundary, much like a cosmic hologram. Consider a simple hologram on a credit card. It's a two-dimensional surface, yet it contains all the necessary information to project a detailed three-dimensional image. The holographic principle suggests that our entire three-dimensional universe, with all its stars, galaxies, and even black holes, could be a projection of information encoded on a distant two-dimensional surface, perhaps at the very edge of the cosmos. Applied to a black hole, this means the event horizon itself is not just a boundary, it is a cosmic hard drive, meticulously storing every bit of information about everything that has ever fallen into the black hole. The story of the universe's past, once thought erased, could be preserved, not inside the black hole in some unreachable singularity, but on its surface. This notion completely redefined what we thought a black hole was, transforming it from a simple devourer into a cosmic projector of information. The stakes in this intellectual drama could not be higher, as the very soul of physics hung in the balance, a captivating struggle to unify our deepest laws and finally understand the true nature of reality. The information wars, a clash of titans over the very soul of reality, had raged for years, but the most profound insights often emerge from the most unexpected corners. While giants debated the fate of vanishing cosmic stories, a young graduate student at Princeton in the early 1970s, a quietly brilliant physicist named Jacob Bekenstein, was piecing together a revelation that would forever alter our understanding of black holes, and indeed, of information itself. He approached the problem not through the lens of quantum foam or space-time curvature alone, but by a deeper contemplation of entropy, that fundamental measure of disorder and information in our universe. Bekenstein's discovery, born from a series of elegant thought experiments, was nothing short of astonishing. He determined that a black hole's entropy, its measure of information content, was not proportional to its volume, as one might instinctively expect for any other object, but instead to the surface area of its event horizon. This was a radical departure from conventional physics. Think of a library. The total amount of knowledge it holds is clearly proportional to its volume, the sheer number of books it contains. But Bekenstein suggested that for a black hole, the cosmic library, its information capacity was instead defined by the area of its outer surface, as if all the wisdom of the universe were etched onto its boundary. This was the first concrete mathematical hint, a crucial clue, suggesting that information swallowed by a black hole wasn't being lost into some unreachable singularity at its heart, but was somehow meticulously stored, imprinted, and preserved at its very edge. This singular idea forged a powerful, almost mystical connection between disparate fields, the abstract mathematics of information theory, the chaotic dance of thermodynamics, and the grand, sweeping curves of gravity. It implied that the event horizon, once seen as merely a one-way cosmic membrane, was in fact a vibrant, active surface, a cosmic hard drive holding the universe's most precious data. It was this startling insight, this seemingly simple formula relating entropy to surface area, that laid the crucial groundwork for the audacious holographic principle, hinting that our three-dimensional reality might, in some fundamental sense, be projected from a two-dimensional surface. From this fertile ground of Bekenstein's boundary emerged one of the most compelling potential resolutions to the black hole information paradox, the fuzzball model. Championed by Samir Mathur at Ohio State University since the early 2000s, this string theory-derived proposal boldly reimagines what a black hole truly is. It discards the terrifying singularity, that infinitely dense point of no return, and the sharply defined event horizon that surrounds it, replacing them with something else entirely, a tangled, vibrating ball of fundamental strings. This fuzzball possesses a definite, albeit fuzzy, surface that effectively takes the place of the event horizon. To visualize this, abandon the image of an empty void leading to a crushing point. Instead, envision a black hole as a chaotic, intricate ball of quantum yarn, composed of the universe's most basic constituents, fundamental strings. When matter, be it a star or a single particle, falls into this model, it doesn't get crushed out of existence into an infinitely small point. Rather, its constituents, protons, neutrons, electrons, are transformed, unwound, and converted into more of these fundamental strings, adding to the fuzzball's already immense complexity. The information those particles carried, their unique story, isn't destroyed. It's intricately woven into the ever-growing, vibrating tapestry of the fuzzball itself. Crucially, a fuzzball is a physical object with a definable structure and volume, unlike the dimensionless singularity. This means it can store and radiate information in a way that aligns with quantum mechanics. Consider a piece of burning coal. It radiates heat and light, but the information about its original structure, the tree it came from, the precise molecular arrangement, isn't truly lost. It's encoded in the properties of the vast number of photons and particles it emits, even if that information is scrambled and incredibly difficult to decode. Similarly, a fuzzball, through its thermal radiation, preserves information. The specific quantum state of the outgoing Hawking radiation, though seemingly random to us, is in fact carrying away the unique information about everything that fell in, resolving the paradox in a surprisingly elegant, if profoundly mind-bending, way. The black hole, in this view, is not a destroyer of information, but a cosmic reencoder, a vast, vibrating repository of cosmic memory. The cosmic fabric, once thought to have been meticulously restitched by the holographic principle, seemed ready to finally preserve the universe's most precious stories. The idea that all information about a black hole's interior could be encoded on its two-dimensional surface offered a profound resolution to the information paradox. But just as the scientific community dared to breathe a sigh of relief, a new, terrifying crack appeared in this elegant solution, threatening to unravel everything and bring down the very foundations of physics. In the year 2012, a quartet of brilliant physicists, Ahmed Amheri, Donald Meroff, Joseph Polchinski, and James Sully, collectively known as the AMPS collaboration, unveiled a thought experiment so unsettling it sent shivers down the spines of quantum gravity theorists worldwide. Their argument, stark in its simplicity, yet devastating in its implications, was this: if the holographic principle truly holds, if every unique bit of information about matter and energy swallowed by a black hole is meticulously imprinted onto the event horizon, then the fundamental laws of quantum entanglement demand a horrifying consequence. Consider entanglement, that quantum oddity Einstein famously dubbed spooky action at a distance. It's the bizarre connection between two particles, no matter how far apart, where measuring the state of one instantaneously determines the state of the other. It's as if two coins, flipped simultaneously on opposite sides of the galaxy, are somehow inextricably linked, such that if one lands heads, the other must instantly land tails. The AMPS team realized that for information to escape a black hole via Hawking radiation, entanglement must be maintained between particles that fall in and those that escape. However, the holographic principle, by forcing all information onto the boundary, implied a conflict with this necessary entanglement at the horizon itself. Their logic led to an inescapable conclusion: the event horizon, that once smooth, one-way membrane, must instead be a firewall, a blistering, intensely hot wall of pure energy. Any unfortunate astronaut attempting to cross this boundary, seeking to discover what lies beyond, would not experience a peaceful descent into the void. Instead, they would be instantaneously incinerated, vaporized into a cloud of elementary particles by a superheated barrier of quantum energy. To put this in perspective, imagine a wall so intensely hot, so violently energetic, that it would instantly disintegrate anything touching it, far beyond the temperature of our sun's core, which burns at a staggering 15 million degrees Celsius. This firewall would be an unfathomable thermal inferno at the very edge of reality. This horrifying prospect directly collided with one of the most sacred tenets of Einstein's general theory of relativity, the equivalence principle. This cornerstone of modern physics states that gravity is indistinguishable from acceleration, meaning that falling freely through space-time should feel exactly like floating peacefully in empty space. An astronaut crossing a black hole's event horizon, according to Einstein, should perceive nothing unusual, no jolt, no barrier, just a smooth, inexorable journey into the unknown. The firewall paradox shattered this elegant simplicity, presenting physicists with an impossible, almost cruel dilemma. They were forced to choose. Either Einstein's cherished general relativity was fundamentally wrong at the black hole's edge, or the inviolable laws of quantum mechanics, particularly entanglement, were incorrect, or the very vacuum of space, which we assume to be empty, was in fact teeming with hidden, violent energy. It was a crisis of profound magnitude, a true Gordian knot for theoretical physics. Yet, from the crucible of this new paradox, a new, even more speculative and profoundly exciting solution began to emerge. In the year 2013, Leonard Susskind, the indefatigable champion of information preservation, joined forces with Juan Maldacena, another towering figure in theoretical physics, to propose the ER equals EPR conjecture. This audacious idea posited a shocking equivalence between two seemingly unrelated concepts that both emerged from Einstein's groundbreaking work. EPR refers to the Einstein-Podolsky-Rosen paradox, the famous thought experiment that first highlighted the mind-bending nature of quantum entanglement, that spooky action at a distance, where two particles are inextricably linked regardless of separation. ER, on the other hand, stands for Einstein-Rosen bridges, better known to the public as wormholes, theoretical shortcuts through space-time, tunnels that could connect vastly distant regions of the cosmos. The ER equals EPR conjecture proposed something truly revolutionary, that every pair of entangled particles, those mysteriously linked quantum twins, is in fact connected by a tiny microscopic wormhole. Do you perceive two particles, separated by light years, influencing each other instantaneously? The conjecture suggests it is not merely an abstract correlation, but a literal connection, a miniature bridge through the fabric of space-time itself. Apply this to a black hole, and the implications are monumental. The information doesn't escape by merely being painted onto the event horizon like a cosmic mural. Instead, it tunnels out, bypassing the fiery wall completely through an intricate, constantly shifting network of these microscopic wormholes. These tiny bridges would directly connect the black hole's interior with the outgoing Hawking radiation, allowing the information to flow out, albeit in a highly scrambled form, without violating the equivalence principle or incinerating an intrepid explorer. It suggests that the very act of entanglement is the creation of a tiny, traversable wormhole, a pathway for information to move, unseen and unhindered, allowing the universe to ultimately keep its cosmic stories intact. After decades of intellectual combat, of fierce debates, echoing across the halls of academia and through the digital corridors of scientific forums, we arrive at a profound, almost paradoxical realization. Our journey into the heart of the cosmic unknown, a quest to understand black holes, has led us to a stunning conclusion. The question itself, what is inside a black hole, was perhaps never the right one to begin with. The true enigma, the central mystery that has driven generations of physicists to the brink of despair and triumph, has always been something far more fundamental: what happens to the information, the unique story, the very blueprint of the universe itself, when it encounters the ultimate cosmic devourer. From the earliest, almost naive conceptualization of a dark star by John Michell in the late 1800s, a simple Newtonian trap for light particles, to the terrifying space-time warping rupture described by Albert Einstein's general relativity and Carl Schwarzschild's solutions, our understanding of these objects has evolved dramatically. They are not merely super-dense celestial bodies, they are profoundly complex quantum objects, challenging the very fabric of our physical laws. What began as a curiosity about gravity's ultimate power transformed into a grand battle for the preservation of information, the bedrock principle of quantum mechanics. Today, the leading hypotheses about what lies beyond the event horizon, and, crucially, what becomes of the information that falls in, are not so much competing theories as they are different languages attempting to describe the same profound, mind-bending reality. Could the interior truly be a fuzzball of vibrating strings, a tangled, intricate ball of cosmic yarn where matter is re-encoded into new, fundamental constituents instead of being crushed to an infinitely small point? This model suggests that the black hole's surface, fuzzy and complex, is where the story of every infalling particle is meticulously woven, not destroyed. Or perhaps reality itself is holographic, as proposed by the holographic principle, an idea rooted in Jacob Bekenstein's startling discovery that a black hole's information content is proportional to its surface area, not its volume. In this view, all the information about the black hole's three-dimensional interior is perfectly encoded on its two-dimensional boundary, like a cosmic hard drive constantly updating its data. This means the story of every star, every planet, every fleeting particle that ever crossed the threshold is preserved, not lost, but imprinted onto that cosmic membrane. Consider the sheer scale of this. A black hole with the mass of our Sun would encode an amount of information so vast it would dwarf the combined digital data of every computer, every server, every smart device ever created on Earth, storing it all on a surface roughly 5.9 kilometers in diameter. Then there is the possibility of a chaotic nexus of tiny space-time wormholes, an idea gaining traction from the mind-bending ER=EPR conjecture. This suggests that the quantum entanglement between particles, that spooky action at a distance, is literally a connection through microscopic wormholes. If so, information might not just be smeared onto the surface or re-encoded within a fuzzball. It could be tunneling out, escaping through a labyrinthine network of these minute cosmic shortcuts, directly connecting the black hole's interior to the outgoing Hawking radiation. This offers a potential pathway for information to flow, albeit in an incredibly scrambled form, without violating the fundamental principles of either relativity or quantum mechanics. What this journey reveals is that the black hole is far from a simple void, or a destructive monster that permanently deletes cosmic history. Instead, it appears to be the universe's ultimate data compression system, a place where the intricate tales of stars and galaxies, of every atom and every photon, are not erased, but meticulously preserved and transformed. It represents the final frontier of our knowledge, a cosmic crucible where space-time, matter, and information are melted down, reforged, and re-emerge in a new, enigmatic form. It is a profound, almost poetic thought. The black hole, once considered the ultimate end, might instead be a library of cosmic memory, a repository where the unique story of every star, every planet, every particle that falls in is not annihilated, but conserved, written in the intricate, arcane language of quantum gravity. This is a language we are only just beginning to decipher, a cosmic Rosetta Stone that promises to unlock even deeper secrets of our reality. The true nature of what's inside remains shrouded in the deepest scientific mystery, a challenge that pushes the very limits of human intellect. Yet, the relentless quest to uncover its secrets has already revealed more about the fundamental nature of our own reality, about the universe's unbreakable accounting ledger for information, than we could have ever imagined.